Assalamualaikum and hello everyone. In the last lesson, we found the modulus and argument of complex numbers. Now, we'll use both of them to write a complex number in polar form. Polar form helps us represent complex numbers in terms of their length and direction, just like we describe a vector using magnitude and angle. Let's look at definition 1.8. If z equal to a plus bj, then in polar form we can write z equal to r times cos theta plus j sin theta. R is equal to the modulus of z, or also you can say a magnitude, and theta is the argument of z, which is the angle. So instead of describing z by its coordinate AB, we now describe it as r theta. This is just a change of coordinate system from the Argand diagram of AB to polar of r theta. This means every complex number can be described in two equivalent ways: standard form and polar form. They represent the same number, just written differently. Let's try example 1.13 together. First, find the modulus. So the modulus is the square root of 3 squared plus 4 squared, which is equal to 5. Next, find the argument. For the argument, theta equal to arctan 4 over 3. So notice that the real and imaginary value both are positive, so they fall in the first quadrant. So 10 arctan 4 over 3 is equal to 53.13, which is actually should be taken directly, right? So let's assume that it is here. So this is the first quadrant. So this is where the theta should be, and we should take it directly because it is from the positive x-axis. Okay, so 53.13. So z equal to 5, which is the r, times with cos 53.13 plus j sin 53.13. This is the polar form, right? Same point 3, 4, but now described using r and theta. Now let's see why polar form is so useful. Look at definition 1.9. If two complex numbers are written as Z1 like this and Z2 like this, which is both are in polar forms, then the multiplication and division becomes super easy. For multiplication, we just multiply the magnitude and add the angle. For division, we divide the magnitude and subtract the angles. Let's try example 1.4 and see how simple this become. For A, let's try to do the multiplication. So we'll just multiply the magnitude of 8 and 4, which will give us 32. And we then add the angles, 25 with 60. So we will later have cos 25 plus 60 will give us 85 degree plus J sine 85 degree. So this is the multiplication of two polar forms, which is quite direct, right? Next, B, division. So to answer this, we don't need to do any conjugation at all. So we'll just use the properties, divide the magnitude. So 16 over 2, which will give us 8. And then for the angles, we should subtract 75% with 15, which will give us 60 degrees, sorry. So cos 60 degree plus J sine 60 degree. So that is the answer for the division. Much faster than multiplying or dividing through the standard form, right? Let's look at C for a bit. If we divide with larger angles like this 72 degree minus with 1 to 5, we get a negative result. But remember that angles are periodic. For example, right, the total angle is 360. So when you get negative answer like this, negative 53, okay, when you get negative 53, you'll just subtract this to get the side of the positive angle. So negative 53 angle is actually equal to 307. So if we can write it, if you want to write it in positive, we can write 307 degree. That's why sometimes your calculator shows a negative angle, but it's still correct. Now move to exercise 1.5 to practice. Try converting between A plus Bj and polar form, and test the multiplication or division using r and theta. But make sure you find the quadrant correctly before calculating theta. So to summarize this topic, polar form is a form of z equal to r cos theta plus j sin theta. For multiplication, we divide the we multiply the r of the two polar forms complex number. For the theta, we will add the two polar form. For divide, we will divide the magnitude of the r, and for the theta it will be subtracted. Conversion between forms helps simplify many operations. Next, we'll move to 1.6, the exponential form of complex numbers, where we'll see how Euler's formula makes this even simpler. Thank you.